Hi everyone, welcome back to another Calculus 12 video. We're doing 4.2 today, maximum and minimum values. And I'll just start off with a quick introduction. If you take a look at the diagram over on the left here, it looks kind of like an upside down parabola. And it's just showing a maxima a maxima occurs when the slope changes from positive. So if we look at this, the slope on this side would be positive. And as we move from left to right, again, the same way we would read a book, that's how we read a graph. As we go to right, it's changing to a negative slope. So if we were to take the slope this way, we can see that it's a downward trend. And that's when a maximum occurs. And maxima, of course, is just the plural of maximum, which is what you're used to seeing. On the right here, it's the opposite. So a minimum or minima occur when the slope changes from negative. So if we start here, we have a negative slope, and as we move towards the right, we can see that it's going upwards, and we then have a positive slope. So that's how minima occur within a graph. Maximum and minimum are called critical values. So I feel like this is new vocabulary. You likely haven't heard of this before. I know you're familiar with maximum and minimum, but you probably didn't know that together we call them critical values. And tying that in with the stuff that we've now learned, we know that those occur when our first derivative is equal to 0. Or when our first derivative is undefined. So again, in this chapter, I told you last day, there's a lot of vocabulary and new concepts to memorize or to learn or to know, and this is another one of them. So know what critical values are and how to find them. So starting off with our first example, so you can see this in application, it says find the max or min of this function f of x equals 3x squared minus 6x plus 5. Okay, so looking at this, based on past knowledge, we know that it's a quadratic equation. We know that this shows a parabola that would open upwards because we have a positive lead coefficient. Okay, so we know that, it's going to look kind of like this. So helpful to have that in mind because that sort of guides us with what to do. So let's look at the critical values by finding the derivative of this. So f prime of x equals, and when we take the derivative, we know the power rule here would give us 6x. That deals with that part. And then the power rule here would leave us with just minus 6, and the last one was a constant, so we know it's just a 0. So we found the critical values. Now we set it equal to 0. That's our next step. So this is how we figure out what is going on and what we're working with. Okay, so when we set this equal to 0, I bring over the 6. I'd have 6 equals 6x. When I divide both sides by 6, I'm not going to actually do it. Divide that by 6 like that. We know that we would get, I'm just getting lazy, x is equal to 1. And that would be our example of our critical value. So there's only one critical value in this particular case. This would be our critical value. And critical value at x equals 1, and we know that this would be a minimum. We knew that already because of this thing here that we sort of drew out that now looks like a smiley face, but we knew that we were dealing with an upside down parabola, so we already knew that anyways, but we could test values to the left and right of that critical value and tie in the stuff we learned yesterday to help us to find out for sure. So let's take a look at another example. In our next one here, we have this function, f of x equals x cubed plus 2x squared minus 5x minus 6. We again want to find our derivative. That's our first step because it's saying to find the maximum or the minimum. So again, we can do 3x squared plus 4x minus 5 when we take the power rule on each of these terms. And you know the last one was a constant, so it's just going to be 0. So again, we would want to set our critical values or set our derivative equal to 0. And we would have 0 equals 3x squared plus 4x minus 5. So now, in an ideal scenario, this would factor out perfectly. And oftentimes it does, but I've chosen one where it doesn't, just so we get to brush up on some old skills. So we do have a quadratic here, but we're not able to factor it. Like I would look to see what multiplies to negative 15, because of this and this together combined, and adds to 4, and it's not going to work. So in this case, just a reminder, we would use our quadratic formula to plug in our A, B, and C values to figure out what this would be equal to. So remember, it'd be negative B plus or minus the root of 4ac, b squared minus 4ac, so we get 16 minus 4. Our a value is 3, our c value is minus 5. I've run out of room there, but you know how this works. All over 2 times 3, because it's all over 2a and our a value is 3. So there's a little bit of review built in, but this guy here, what I've plugged in, is simply us applying and using the quadratic formula. I'm going to assume that you all know how to simplify this, plug it in, and work with this, and I'm just going to tell you to make this easier. We'd have negative 2 after I clean everything up and simplify it, plus or minus root 19, all over 3 because I'm canceling things out and simplifying top to bottom there. So this is telling us where our critical values are. So in order to find the maximum and the minimum, I would want to break up my graph into different regions. So this is basically just like the stuff that we did last day or in section 4.1. And so maybe I'll just briefly show you over here. You don't actually physically have to do this and graph it out, but I'll just show you so that it's super clear to you where this is all coming from. So I would take this and say, okay, if I have my negative 2 minus root 19 over 3, that's this dotted line here, I would want to test something to the left of that point. And then that's really close to this negative 2 and negative 1, and I could say 0 is there. And then I could draw another one here to find the positive version of this. So negative 2, I feel like I should color code. I've been lazy with the color coding, so let me do that here to try to make this easier. So let's say this is my negative 2 plus root 19 over 3. And again, I'm just wanting to pick values that are around here. To the right of that would be the number 1, 2, on and on. So just so you can get a sense of where this is, and you could punch this into your calculator, the root, like all of this stuff to get an idea, and or if you find it easier to work with decimals, but I wanted to show you where I'm getting this from so you can clearly see what's happening. I'm just going to quickly recap what we've done here. If I'm looking for the max and min of this, we found the derivative, because we're looking for the critical values. We set the derivative equal to 0 to find the critical values. I found 2 of them here because of this plus and minus part, and I took the 2 critical values and I've plotted them here and here, and then I'm breaking this up into 3 regions. So I'm going to say 1, 2, and region 3 to test to see where it's positive or negative. And then I'd want to take some values from these different regions. So let's say region 1, and I would want to take some value. So if this is negative 2 I'd have -3, -4, and on and on. So I'm going to pick x equals -3, and I would plug that into my derivative that I found here. So I would plug into that my -3 to see if I had, so 3 times -3 squared plus 4 times -3 minus 5. When I plug that in, I get a value of 10, which is greater than 0. So I know here my value is increasing. So that helps me with the first portion. Okay, in my second portion, I have options, but do you guys see that 0 is probably the easiest one because 0 is so nice and easy to work with? So again, I'm doing f prime of 0, and I'd plug it into this formula here. So 3 times 0, blah, 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 blah. When I plug that in, you'll see why I chose it. Basically, anything with an x there gets wiped out. It leaves me with -5. So, since -5 is less than 0, I know this is decreasing. Okay, so hopefully you're getting the hang of what I'm doing here and why I'm doing this. And in the third one here, let's say I want to pick 1 just because it's easier to work with. The goal, I can pick whatever number I want in each region. I like to pick the easiest one. So again, I'm going to do f prime of 1. So again, in my formula here, I'm simply going to plug in 1. And when I do that, I get that it's equal to 2. And I know that 2 is greater than 0. So I know that this is increasing here. So it's increasing, decreasing, and then increasing. So this gives me an idea of what is going on there and what this might eventually look like. So I'm going to just quickly, it didn't ask for this, but I want to quickly show you and get a sense of what this would look like. So if we were to sketch this out, it's showing a slope that's increasing and then decreasing and then increasing. So I know that it's sort of showing this shape here. And on this shape here, I know that at this point, that was my critical value. So the critical value is where the slope is 0. So I'm hoping you're able to sort of tie this in with past knowledge. This would be at the point -2 minus root 19 all over 3. And at the bottom here would be my minimum value. And that would be happening at the point where I had -2 plus root 19 all over 3. So this would be my max, and this would be my min. And you can see the idea of how we came up with that. So after all this work, there's our answer, and there's our answer. And you didn't have to show me that on a graph, but I wanted to make sure that you were making those connections between the algebra, the breaking it up into regions, and then the sketching it out. And to be clear, I drew the graph off to the side separate from this, but we could have actually have just done it on the number line we had already done here, which would also be able to show you the same sort of trend. Okay, so just one other quick concept that I want to point out, and that is global versus local maxima and minima, because I think that you're used to seeing global max and min, but I don't know if we've talked about the distinction or the difference between these. So I just want to use this to quickly point things out to you. If we take a look at this colorful graph that's drawn here, if we are to look and compare at the different values and the things that are going on here, so if you take a look at it, we have a local maximum here at point A, here at point B, and here at point C, and up here at point D, it shows that it keeps going. So those are all local maxima. We have different maxima at different areas or different regions. G down here, and H down here, and even F and E would all be example of local minima or local minimums. And so if you're finding the global minimum, you would take the lowest one. So in this example, E would be the lowest one because it also indicates that it keeps decreasing. So basically the only idea or concept behind this is that the local max and min is what it sounds like. It's just within that little region. So for example, if we're looking in here, the local maximum there would be C. But if we're looking at the entire thing, the global maximum, we would say is D because it keeps going and it's the arrows indicate that it keeps expanding. Okay, so you can do page 176, 1, 3, 4, and 6. Those of you who are doing this online, you can do every other question, so skip each letter. And I hope you found this helpful.